when you capture a discrete signal, you need to make sure you use an appropriate sampling rate, otherwise a phenomenon known as aliasing is introduced. Now, aliasing basically manifests itself as introducing what I would describe as undesired or unwanted frequency components. So the aim of this video is for you to understand this statement. Okay. Now, aliasing does relate to a choice of sampling rate, and at this stage you should be aware that if you have a fast changing signal, you will need to sample it at a higher rate than a signal that changes more slowly. So I just have a couple of examples to highlight that fact. So here I have two signals. The signal up at the top is changing more slowly than the signal at the bottom. Now if I was to sample the top signal at a certain sampling rate, and I'll just choose it by hand and just choose a rate that I think would visually represent this signal quite well. Okay, so there's a sampling rate that seems to be pretty good. Whereas if I use the same sampling rate for the signal at the bottom, um, I would not capture the signal faithfully. Okay, and by that I mean if I was to interpolate between these samples, or in other words draw a line between the pink samples, I wouldn't get a good representation of the original signal. Because remember, when you sample, all you have basically are the pink dots, and what you're trying to do is interpret what those pink dots mean. And what we do is basically draw a line between those pink dots. So if I drew a line, interpolated between those pink dots, what I'd get is a signal that looks like this blue signal, which isn't a good representation of the original signal. Whereas if I did the same up here, I'll just do it roughly, what I would get is a very good representation of the original signal. Now if you choose the ideal sampling rate, you'll get an exact representation. But we'll get into that a little bit later on. Okay. Now, what I'm going to go through now is the choice of sampling rate when you're dealing with sinusoids. Okay, so I'm going to show you an example of sampling a sinusoid. Now the reason that I do that is because all signals are made up of sinusoids. And I've done a video earlier on that, demonstrate that all signals are made up of sinusoids. Now, if you can appreciate that, if the next part of this video in which I deal with the sinusoid, you'll be able to appreciate how aliasing is introduced into more complex signals because, as I said, all signals are made up of sinusoids. So here I have a sinusoid. Its frequency is 1 Hertz, okay, which makes this 10 seconds here. So it's a 10-second segment of a sinusoidal signal, because we've got 10 cycles there. So each point here on the axis is 1 second. So that's 1 second, 2 seconds, 3 seconds, 4 seconds, etc. Okay, and if I was to capture this signal faithfully, I'd probably use a. Let me change the color there. I'll use pink instead. If I was to sample that signal at this rate, so I'm just going to use what I would describe as an appropriate rate. It seems to be an appropriate rate. And I'm doing this very roughly, just for a couple of cycles. Right, I think I'll leave it at that. So I'll just clear away the sinusoid. So if I sampled at the rate shown, what I'd have are these pink dots. And if I interpolated between those dots, I would get this signal. Oops, that'll do. Okay, and you can see that that is a pretty good representation of the original signal. Now it's all very roughly done, of course, but I hope you um, understand what I'm trying to achieve. But you can see that it's a good representation of the original signal. Now, let's take a look at what happens in the event that I don't use an appropriate sampling rate. Just need to clear all that. And what I'm going to do now is use a sampling rate of 1.2 seconds, or rather a sampling period of 1.1 seconds. So I just have a grid line because I want to do this reasonably accurately. You may not see these in the videos, but I just have a grid of points that are separated by 1.1 seconds. So that point there is 1.1. That's that's 2.2. This point here is 3.3, 4.4, etc. Okay, and what I'm going to show you is the sample points that are result if I use this sampling period of 1.1 seconds, which is an inappropriate rate. And visually we can see that it's an inappropriate rate. So these are the points that I will pick up from my signal. Okay, just bear with me for a second. So these are the sample points that are obtained if I sample the signal at 1.1 seconds. Okay. Now, I have one more point here. Just throw that in there. So the blue line, of course, is my original continuous signal. The pink dots are what I will obtain if I sample that signal at a sampling period of 1.1 seconds. So what I'd be left with are these pink dots. Now if I was to interpret these pink dots and I had no other information about the signal that I sampled, I would say that the signal that I sampled was this signal. And you can see that the signal that I'm sketching out here is in fact a sinusoid. It's got a sinusoidal shape. Now if I continued on the sampling of my original blue signal, this of course sinusoid would continue on forever as well. But it is a sinusoid of a different frequency. So even though the signal, the original continuous signal, was a sinusoid of a certain frequency, the signal that has been captured, essentially, the discrete signal that I've captured, is a sinusoid of a different frequency. So it's not the frequency that I really want. It's a sinusoid that doesn't have the frequency of the original continuous signal. So it's effectively what I've done is introduced an undesired or unwanted frequency component due to the fact that I use an inappropriate sampling rate. Now, in the next few videos, I'll take a closer look at aliasing from a more mathematical view and to take a look at it in the frequency domain view. But this is the key point of this video. I want you to appreciate that if I sample a signal, so this blue signal, at an inappropriate sampling rate, then what I get is a sinusoid of a different frequency. Or rather, I should say, if I sample a sinusoidal signal at an inappropriate sampling rate, what I introduce is another sinusoid. It's still sinusoidal in nature, but it's of a different frequency. Now, the reason why I'm focusing on sinusoids is because all signals are made up of sinusoids. So if you can understand this point here, you'll start to get a handle on aliasing. Okay, thanks for your attention.